So why don't we? Yeah. Okay, so it's my honor to introduce Dr. Xuesong Zhou. And Dr. Zhou is a professor of transportation systems at the School of Sustainable Engineering and the Built Environment, Arizona State University, ASU, Tempe, Arizona. And he's also the director of transportation.
You don't need to wait further, because Professor Daniel is here, so
Yes.
really, he's another external former student and a follower of his scholarly work.
Yeah. So just very briefly, Dr. Zhou's research focusing on developing methodological advancement in multimodal transportation planning applications. And Dr. Zhou himself has published over 100 journals in transportation Part B, Part C, and other important transportation research journals. And he is currently serving as the editorial board member of Transportation Part B. He also served as the associate editor of Transportation Part C. Currently, he's also the committee chair of TRB's Transportation Network Analysis Committee. And his talk today is titled Dynamic Recovery Capacity Modeling for Multi-Sector Urban Infrastructure, Traffic Flow, and a Low-Rank Structure Perspective. Besides that, I want to say that Dr. Zhou has long history and friendship with UC Berkeley ITS professors and researchers at PASS. I'm pretty sure he will talk a little bit about that today. Without further ado, let's welcome Dr. Zhou.
Okay, so I can just speak directly to the speaker, right? So let me share this one. Okay, so thank you so much. Thank you for this opportunity for inviting me here, because I know that I always had a special place for Berkeley because traffic flow theory, much of the traffic flow theory is really developed here in Berkeley. So today, in fact, I try to show some learning curve we have, how to apply traffic flow dynamics or the traffic flow theory to the related area of resilience and discovery how a city can recover from disruption. So I would like to really mention that this work has the collaboration with my current student Alicia Tang and other professors at Arizona State University, and is sponsored from NSF. Okay, so I will go very quickly, motivation. And then I try to apply a multi-resolution micro, meso, and macro level traffic flow to the recover model. So the goal is quite simple. The traffic flow has its own understanding. The traffic flow theory provides a very unified mathematical language to describe the flow dynamics. So I try to just apply what we learn and then using the framework to discover the way to describe recovery. So I'm using one motivating example, 2011 Japan earthquake. So here is the data set we have. Is the x-axis is a different time of day, and then we do see the different sectors such as airport, bullet train, expressway, local train. They all recover in different way, but in a very similar curves. So what I try to promote here is we need to understand all the fundamental property from the notion of recovery curve or fundamental diagram of recovery. So on the right, I do show we have the initial elastic response from the material science, and then we have yield point or the capacity point, and then also we have the different adaptive recovery process. So here I try to just show step by step how the different urban systems can have the similar disruption recover pattern and then establish the traffic flow theory in this area. So the question is, can we try to describe all the similar behavior after the shock? The answer is yes. So here on the left, we do see these 70 plus years of traffic flow theory coming from Professor D'Angelo, Professor Nuo, and here I try to show the capacity. I try to show the free flow speed in this volume density curve. Then we have really calibrated all these fundamental diagrams using different data set. The different models provide the different measure, the different calibration results. But more importantly, I try to highlight here is when we try to understand such a system, we do need to understand, number one, there's a capacity constraint. Number two, we can relate it to this traffic flow dynamics to the queue-based understanding. And also we have free flow versus congestion. We have the different discharge rate. So it's a multi-regime behavior. Then the last point is when we have multiple dimension of the data, we need to use the low rank property to capture the structure difference of all this underlying behavior. So again, I try to show my learning curve. In the next few more slides, I will talk about car following model, set transmission, the queue model or set transmission models, set representation, and also the fundamental diagram and my own area of network control. But I try to show that in parallel, in the resilience, they need to study the similar multi-resolution behavior to understand how the individual disrupted unit, such as the vehicle or trajectory or community, how they can recover. Do they have a healing capacity? Do they have this disruption recover geometry? And then how the different sectors respond in a different way, but in some kind of fundamental diagram. So this is my mapping from traffic flow across different scales and all the way to the recover dynamics. I will touch all the different points individually, so please allow me to go to some fundamentals. So again, Professor D'Angelo is great for you to give me a lot of education. Here on the left, this is a space-time trajectory. This is one of the virtual queue mapping to the physical queue. And I don't need to go through all the details. I try to just show that from the individual vehicle, from the free flow to congestion, then you have this virtual waiting time. As I try to show in my mouse here, is a virtual waiting time. And Professor D'Angelo and his former students in 1997 provide very elegant theory to map virtual waiting time to physical waiting time, and then develop set transmission model for us to compute all the kinematic wave propagation much more easily when the demand is greater than supply. Then another thing I learned from the school of UC Berkeley's traffic flow scholars. So you can see here is NGSync dataset with a time and the space diagram. And then there's a shock wave. And then along the shock wave, we also see different trajectories. So when there's a merge or lane change in behavior, there will be a disrupted trajectory. So from there, we should be able to understand a vehicle here could be viewed as a disrupted unit. Flow could be viewed as a recovery rate. Density is a bad log due to the disrupted capacity. Then the capacity point in the fundamental diagram could be related to the healing capacity, the maximum healing rate in our fundamental diagram. So I try to just show I do make an analogy, but in the next few more slides, I try to show the analytical forms for the different cases. So I had to just look at one person, one workplace, consider one disrupted unit. Here, this is all, this is a very old school COVID-19 data set, but it has a different sectors. This is a Google mobility data set with activities related to parks, recreational, grocery, and pharmacy activities. So all of these have disruption and has a recovery, and this kind of disruption recover is the return to normal as our traffic flow. In our traffic flow, we have the breakdown, and then it will take some time to return to normal. And then here in our analysis, we try to ask a question is, suppose this entity is a community or activity type is disrupted at the time t, how we can model its instantaneous property of recovery. I have to say there are three outcomes of this recovery. The recovery back to the normal, the recovery of the transition loss, and the transition gain. To make it clear, I draw a baseline, as you can see here, 100% of the normal baseline. After COVID-19 or after any major disruption, we do see transition loss and transition gain. So here I try to show the transit station, San Francisco, California, we have still dramatic transition loss, and then how we can use a different incentive to improve the transit service or to improve the attractiveness of the transit to reduce this transition loss is always a good topic to study. In comparison, in Arizona, the transition loss is less dramatic. So we introduce this hazard function to study the proportion or fraction of the population being disrupted at the time t. So I just try to quickly highlight that the hazard function is a cumulative recovery function in this analogy, and then we can try to develop the density of the recovery time. We can also define hazard. Here, even as a hazard, in fact, I mean the opposite, instantaneous healing rate, which is a ratio between the recover ratio divided by the cumulative recovery rate. So in the traffic term, the h of t is similar to a flow rate for the individual recovery event. So the simplest hazard function is exponential function, and the exponential function has a constant hazard rate. But in our discovery, for learning all the community recover, they have a fundamental diagram. The fundamental diagram has three terms: initial healing density, the time to peak healing, and the shape parameter. So essentially, if you just look at the hazard function, it's very similar to our fundamental diagram with a free flow speed, capacity point, and the breakdown or this congestion branch. So by using similar forms, we are able to capture these different stages of recovery, because we know for sure if there's a transition loss and there is a static condition, the instantaneous recovery rate will be almost zero. So this is something we need to capture.
Can I ask a clarifying question?
Yeah.
How do you define disruption?
The disruption here is it could be external events. In COVID is really the disruption due to disease, and then in traffic is maybe the traffic breakdown so that the capacity reduced dramatically. And here maybe I'm looking at the time series. So I look at the activity level from the baseline of 100% reduce and then coming back. So I will say I artificially try to just draw a line at this cutoff point. If they before the maximum reduction, I call it disruption. After the maximum disruption, I call this as recovery. So this is my definition. But in reality, actually recovery can happen right after that moment of the disruption. And the disruption can also happen continuously as events along the whole process.
So can I think about it as like an anomalous event affecting travel demand?
Yes, yeah. Here, what I show here is more about traffic demand. Later, I will also show the demand supply that could be both disrupted.
Okay. Thanks.
Okay, so what is similar to our traffic capacity, we need to set the maximum recovery rate. And this is our whole purpose of study, study the discovery, disruption, recovery process, and traffic flow fundamentals. Okay. So by using this curve, we do look at all the recovery rate, and you can see very clearly for the different activity types, residential, transit, workplace, they have the maximum recovery rate. And then from the beginning, because the gradient is 0, so they're always coming from so-called the 0 position. And then to the end, they will reduce to almost 0 because they go to like a stable condition, they just could not recover further, which somehow explain why there's always the transition loss, because transition loss means the recovery rate goes to 0. Okay. So for other experts, they might first apply the exponential model, but you can see exponential model just assume a constant recovery rate. No, we will not be able to capture this shape or this hump behavior. Okay. So I will not spend more time on the individual behavior. Then this is another thing I learned from Professor D'Anghenzo's introduction, fluid queue model. So let's assume we have time axis, we have the flow rate, we have the net flow rate, and this red line is the arrival flow rate, blue line is a departure rate, and then we should be able to see the beginning time of the congestion. So on the very bottom is the Q lines, and also when the net flow equals to 0, this is maximum Q. So Professor D'Anghenzo teach me how to use very elegant method from Professor Gordon Lewis' textbook to do this kind of analytical formation. When I apply this knowledge to the recovery, so you can see on the right, many of those literature just try to use a V-shaped recovery. So when you have a V-shaped recovery, if you look at this V-shaped recovery as a cumulative, say redshift or activity level, if you try to just derive their gradient, then you get almost a linear net flow rate. So by using this, you cannot explain the transition loss, transition gain. So that's why I further extend Professor Gordon Lewis' model to describe the asymmetric disruption, recover. So from here, you can see clearly we are able to do this curve fitting using this analytical model. Using this analytical model, we should be able to describe the time of the disruption, the time of stable condition, and also the corresponding transition gain, transition loss, and the P is the total duration of disruption and the recover. Again, in my disruption, I somehow define as T0 to T2. Okay. And then my recover, I define as a T2 to end of the Q or the end of the transition. And then by using this kind of analytical scales, we can define the D over R or R over D ratio as a recover to disruption ratio. Then we can try to measure how fast a recovery process could be. So this is just a very elementary application of the fluid queue model from traffic flow or queuing model all the way to the recovery process. Then we go to the fundamental diagram. So on the left, this is our free flow congestion region of the fundamental diagram. I try to apply the similar transition, try to just get two things in this curve. One is when we have the major disruption. So the y-axis is a disruption. The x-axis is a transition gain and transition loss. So we see three regimes. One region is an elastic region. Another region is a yield region, which is a capacity region right here. And I try to just show that someone who can understand this fundamental diagram, they could apply this to the strain model. Basically, is more disruption will create more transition loss. But when we try to look at the COVID-19 data set, in fact, that small disruption may introduce some transition gain. For example, for the activity of retail, activity of going to the park, actually we see the transition gain. And that if you try to model in long term, if we try to model in the long term, the transition, maybe we'll speak a little bit closer to this. Yeah. We can try to build a linear relationship between the disruption magnitude and also the transition change. So here we develop a similar fundamental diagram to describe this behavior using COVID-19 dataset. So I think folks here say, hey, COVID-19 is already the history in the past. So let's try to look at other phenomena. So here we are using the extreme heat in Phoenix. We will use the Q-based temperature model. So as you can see here, we can have similar inflow rate as a solar radiation input. We can model the outflow rate as a cooling rate. And then the temperature is accumulated heat energy. So in this way, we can use this very simple model to describe the inflow, outflow, and the accumulation of temperature, or accumulation as a result of accumulation of energy. So by using this kind of analytical tools, we can quickly discover forests that have higher destruction or higher discharge rate, and the urban area, developed area, has a lower discharge rate, so that you will take a longer time to absorb all the heat wave, okay, compared to other land cover type. So we can further try to use this stress strain model. I can call this material science model, but they had a very similar form as our fundamental diagram. Then we will be able to capture the yield point associated with a different land cover. And then this will be quite useful, for example, to know the how many lands should be developed, how many forests we should keep in place in order to counter these extreme heat conditions. So in this graph, the horizontal axis is the relative extreme heat recover duration. So you can see in Phoenix, we have almost 6 or 4 hours of the recovery. And then the y-axis is the given input of radiation energy input. Then after I try to study the 3 different levels, very similar to traffic flow, I will go a little bit deep. I will try to introduce tensor. So we already know a point, a scalar is just one element, and then we have one-dimensional vector, two-dimensional matrix, three-dimensional tensor. In traffic, we understand OD, origin destination matrix, is a two-dimensional matrix, and then the path as origin, destination, and the path flow. Okay, so what I want to say is in the disruptive recovery process, we have many data sets. We have multiple dimensions. We have dimension of region. We have dimension of different activity types. We have dimension of the different commodity types. So we need to have the efficient representation. That is why we do try to use the tensor, all the high dimensional tensor to represent chip generation, chip distribution, mode choice, and recently we try to connect many different tensor blocks together so that we can efficiently use the forward propagation, backward propagation in our computational toolbox. I'm not going to any details. The reference has been provided here, but I try to just show that by representing the tensor at the first place, we are able to provide capability of compression. So I try to just use this image processing as a way to look at the intuition. So you can see here, for the image processing, here is the Lambda image as a benchmark data set with the original picture. They have this rank, the rank as the different dimension, essential dimension structure to capture the spectrum or the appearance of the original matrix. Here, the x minus x hat is the estimated variable, x is the original variable, so we do have residual. So when we try to increase the number of ranks, we have more dimensions, and then we can see the residual will gradually reduced. So this area is low-end approximation is a very active area. Large language model has very similar issue, such as compress all the weight matrix, and then to deal with this low memory or small language model who can perform very well under different conditions. So I try to review the knowledge of single value decomposition SVD. So if you try to look at the image as a matrix, then you can try to apply a SVD with a left triangular and sigma as a singular value, and then the V transpose will be the right singular vector. If you try to understand from our OD demand matrix, you have OD pair, y-axis, you have tan as a horizontal axis, then you can try to represent a U, which is the OD pair to rank or to latent, and then diagonal elements to capture all the essential elements, and then we have a latent back to the 10 dimension. So we apply this very elementary as the first data we can introduce tensor decomposition to capture the structure difference, the structure representation of all the different data set. So since here, we are in Bay Area, so let's look at the BART ridership report. So we have 50 stations. So we have this open data set from BART station to station ridership per hour per day in the last 6 years. So you can see we have a 50 by 50 matrix. Then we also have this all the time horizon. So we have 50 million of the records. So if we apply SVD, then the question is, how many ramps do we have? So first of all, we do look at all these weekday, weekend. We do look at all the other disruption. Interestingly, if we apply the SVD 90, so 90 rank or 90 dimensional matrix is sufficient for us to capture 99% of cumulative energy, or maybe you can call this as a variance, and then has less than 10% or a very small error. So what we try to just come out here is, first of all, when we deal with a very large scale matrix from the demand side, we should be able to capture the most essential demand pattern. If you look at the recover demand we have from our early examples, state by state, agency by agency, different sectors, we also see a very uniform low rank structure for this recover trajectory. We did some elementary study. 90% of variance can be captured by the first rank, which has a different way on the different activity types on the different states. Then the second mode can also explain another additional 4% as this dimension weighting matrix to describe essential chips versus the optional chips. So when we try to push further, you do see we all have a long tail because just using this very simple SVD is not sufficient to capture all these random these structure deviation. The message here is there's a common structure representation. We can try to reduce this kind of demand and recover process. So since we are the traffic network traffic network researchers or analysts, we always want to the demand and the supply. So you already see right here, I try to show a dimensional demand tensor. So this high dimensional demand tensor has its own internal rank, could be 90, could be 10. So typically the demand has a high rank compared to supply. The supply tensor is number of chips we provided, say the frequency for the bus station, and is determined by the average headway leaving from the station at the BART. So let's try to just look at how the demand and the supply has a very imbalanced rank structure or dimensional structure. So what we try to just look at is the timetable, train timetable in BART service. Interestingly, when we try to look at all these timetables, they have either 10 minutes headway from early morning 5 a.m. to 9 p.m. and a 20-minute headway, on other lines. So which means they had a very low rank structure on the demand, on the supply. And then this explains that why the supply should be relatively adaptive or flexible to provide the matching to the time-dependent demand. We can also just look at the reversible lane on the Golden Gate Bridge. Have the early morning peak, the afternoon peak in different directions. So we change the lanes. We have this reversible lane can be viewed as a measure to provide a higher rank of the supply so that we can minimize this structure difference between demand and the supply. So since we're here, we're at Berkeley, I have to just look at Professor Gordon Newell's classical work on matching demand and the supply dynamically. So here is one of the very classical paper on continual approximation in 1973. In this formula, you have cumulative arrival, you have cumulative departure. I don't need to derive all this detailed formula, but Professor Gordon Newell derived that the optimal rate of departure equal to a square root of arrival rate, length of the t. So this is a very significant concept very early on. Then the question for us now is, this is a one-dimensional result. How we can apply this to a multi-dimension of OD pairs, different time period, and different activity types, different service types. So I just try to use this as a motivation for further study this compression method. So recently, we do look at all these optimization through the latent pattern. Traditional method here is we always enumerate all the OD pairs, enumerate all the paths, so we get millions of variables. So if we are able to compress those large number of variables, could be random variables, could be multiple dimensions, such as Uber, such as Waymo, they don't have the regular schedule. So how we can capture this kind of supply, capacity supply in a structural way? So there are many applications to do network design, traffic signal timing, by looking at this latent structure. And this latent structure can capture not just a single day, but multiple days, similarity in our design. Professor Varaya in 2018 has a low-rank approximation method for traffic signal control, which prove we can, by relaxing this fixed timing to be a little bit dynamic, we can reduce the signal delay dramatically, say by 5% or 10% without even going to a fully adaptive signal control required loop detector. So in summary, I try to promote a multi-sector recovery model. At the current stage, we're moving toward a system-level space model. So here, the Y is all the multi-dimensional observation. The X is the latent matrix. So we need to compress the observation to the latent, which is the matrix C here. So this is our single value deposition we try to explain. Moving forward, I just try to show that we are recently working on different data set, Chicago regional data set. We can very quickly compress these path flow variable from 1 million to a magnitude of 10,000, but still reach reasonable solution quality. So in summary, I think now I spend this, yeah.
Going back to, well, were you able to test it at all on the bigger network?
Yeah, I test also Chicago regional.
Same.
Yeah, same base layout. Yeah, Chicago regional has about 30 million paths.
Yeah.
Yeah.
Thanks.
Okay. So I have 3 principles I learned when I try to apply traffic flow dynamics. Principle number 1 is capacity is a dynamic. So we do look at our healing capacity and from our healing capacity diagram. So I hope that more study devoted to healing capacity, just as a highway capacity manual, because a healing capacity is an important indicator for the communities to allocate different resources, for the recovery. Even earthquake, there's unpredicted earthquake events, fault lines. So we just need to enhance our overall healing capacity in response to unpredicted events. Principle number 2, multi-regime behavior. So previously, when we look at the hazard function or the recovery function, people might just simply use a exponential distribution, try to provide the data fitting result. But here, from all these COVID-19 data set, we can see a common thread as elastic yield adaptive, a 3-stage behavior for us to further study. Then principle number 3 is load rank. So because for disruption, there's also the positive feedback loop, such as workplace and the transit. These 2 activities are always connected together. If we have more people work from home, then the ridership of transit will be reduced, and then you have a reduction of the transit service as a part of the vicious circle. We still try to apply this latent factor or the structural analysis, try to pick up is any eigenvalue, mathematically speaking, could give us some positive or negative indicator. Or do we have a vicious circle being observed, particularly after the COVID-19? Now, even after a couple of years, many agencies still had almost 30% transition loss. Okay? And then this is the biggest hurdle for the transit agency to survive in long term. So the last message, as you can see here, is low rank. So we already know traffic is a low rank because we have fundamental diagram, we have wave propagation, we have a conservation law due to the capacity. So we have to just highlight here the recovery is also has a low rank structure because the human behavior behave very similarly, and we have this infrastructure interdependency. So the learning curve I have here is, by using all these foundational traffic flow theory, we should be able to provide more analytical guidance on the recovery planning. Okay. So I don't need to demonstrate all my mathematical equations, but I feel that we should be able to apply many of the know-how from volume delay function, fundamental diagram, conservation law to construct a much more efficient recovery dynamics model. Okay. Future research. So I do have a lot of assumptions in this study. I assume it's some kind of stationary point, but the recovery process never stop. I can only statistically to determine the stationary point, and also all the multi-sector they are coupled together, such as activity of the land use with activity of the travel, and they also have this cascading failure. Some of the transit agencies, they just could not cover, and then they go to the extreme of reduce service dramatically. So I think along this line, I learned quite a bit on the complexity of this recovery process. So the practical use of this study is there's a many climate change, climate adaptation planning. When we say planning, we need to plan for resource, and then the planning of the resource should be attached with capacity allocation. So previously, there's a lot of study talking about recovery capacity, but I think I try to here with my co-authors try to define this capacity more precisely. Then this also related to the long-term infrastructure investment planning and how to prioritize the different investments. I think this is the end of my talk. I try to show my appreciation. Even I graduated from UT Austin. I studied with Hani Mamasani, and Hani's push for us to apply traffic flow physics. Our school actually is coming from there's a traffic flow study all the way to another different branch, but so eventually, I want to just advocate that we need to apply our traffic flow physics to recover behavior. So here, since my former supervisor Hani Masani, he passed away early this year. So we summarize this paper, serving as in memory of all his guidance and pioneering work on dynamic traffic assignment. Okay, so I'm open for questions. Thank you so much.
I have a question. I'm very curious and interested in this low rank part. So I'm wondering, when you do this network optimization and decision making on top of the low rank, like the low rank structure actually depends on the decision that you're going to impose, right?
Mm-hmm.
So how to make sure that you recover that what you are learning is actually the low rank structure of this mapping from decision to demand?
Yeah. This is a very important question. I can only say at the current point, if I just go to the SVD, what I study now is more about linear mapping, for the original variable to some kind of latent value using simplest linear mapping as possible. There's many other studies, such as people are using neural networks in transformer. They already have all the encoding, decoding process.
So, for example, the value function encoded.
Yeah. So here is I think is from just a very basic traffic flow or network design. We cannot simply just use a black box neural network. So it will be very interesting for us to just look at if I use a linear mapping, how much it can compress. Yeah. And then when I try to make the projection back, I do see always approximation error. This approximation error is guaranteed by this SVD approximation error formula. Okay.
I see. So did you find that this, for example, the principal vector or this low rank structure, like how does it depend on the physical network structure, or how like the complexity of the decision-making problem?
Yeah, so I can use my experience here using the path flow, because when we have, for example, Bay Area, 5,000 zones times 5,000 zones.
Right.
So 80% of all the OD pairs are minor. Let's just have 1 or 2 or maybe 0.1 volume going from origin to destination. If I try to enumerate all these 1 million, 30 million paths, then the problem becomes too difficult to solve. Basically, I have to really just get my dominating path first.
Yes.
Then other researchers maybe simply abandon all these not so important flow, but when you abandon these not so important flow, that you just abandon 10% of the demand. And yeah, so we try to just provide a balanced approach to capture the major flow impact, major flow with some reasonable approximation to the minor flow.
Wonderful, thank you.
Thank you.
Any other question from the audience or from online audience?
Sorry, I have a question.
Yes, please, go ahead. And then- Go ahead.
Okay. I'm interested. Hello, Professor Zhou. Thank you for your presentation. I'm interested in the part about large scale optimization. Can you move to that slide? Oh, sorry, can you hear me?
Yeah, we can hear you.
Yeah, I hear you. Yeah, I hear you. Yeah.
Oh, sorry.
Okay.
Oh, yeah. In these slides, you said maybe you can use some latent patterns to deal with origin destination pairs, and then you use optimization methods to control something like traffic signal to solve this problem in a more efficient way because the previous data is so large. My question is, because when you optimize some other things like traffic signal, how to make sure that the OD, the vehicle that obey such traffic signal setting, because the data that you get is just the historical data, it then obey the new traffic timing that calculated by your model. Yeah. Can you
Yes,
you understand my question?
Yeah, I understand. I mainly just work on the offline problem. For the online problem, the transition from the current stage T to the next stage T+1 still we require a lot of data to study. My dissertation was all about OD estimation. I was using Pan's data set in the Bay Area, thanks to Professor Baraya's introduction, and I try to apply this OD estimation common filter. So I just could not comment further because all these transition matrix, if everything become latent, there's something too complex to define yet. I stay my offline for now, but I think you reach a very important point. I think eventually some of the variables you have to just honor all the physical constraints, such as a non-activity flow constraint, such as a capacity constraint, some of the soft constraints, such as variation of inequality, such as gap function. So there's a different trade-off. And here I try to just show that we need to, even for many constraints, we need to just have important constraint and minor constraint, and then to get a sense how we can solve the problem much more efficiently. Because in reality, people are only looking at the main pattern.
Scott?
Yes, I
I
see.
know my answer is not perfect, but
because we usually use traditional methods to solve such optimization problem. In that case, we can ensure that the vehicle obey the physical constraints. But if we introduce using some latent pattern method, something like neural network, it is hard to make sure the constraints are satisfied. So I'm just curious about such question because it is also a very popular topic in this area, I think.
Yeah. I think if I try to add a little bit more information here is when you have this kind of latent factor, you always have the two-way mapping, original value to latent back to original value. Now, once you apply any compression, there's a loss of compression. So So we need to study these for traffic flow, for OD, for path, and then there's a many study using low rank approximation, tensor decomposition, mainly for traffic speed, travel time, for this kind of very direct observation. But for OD flow, for traffic flow control, we need to look at how we can using some analytical representation first, and then later when we use, say, transformer, we get foundation understanding before we use all the fancy computational methods.
I agree. Because when you use latent pattern to control the traffic speed, there are no big concern about the safety. But if you use this pattern in other signal control or boundary control, maybe the safety concern is big than only controlling the traffic speed. I agree. Thank you
And
very
also,
much.
Yeah, another thing here is I think we all know Lagrange generalization. So when you try to just solve any constraint problem, you still need to dualize it, and then automatically you already working on the dual space with approximation error. And I think what I try to advocate here is try to just find the most important OD pair, find or maybe OD pair pattern, or try to find the most important constraints. So try to just look at this kind of spectrum representation. And as opposed to in old days, when we try to solve linear programming, we just use basic variable and basic variable. We are only look at the independence between constraints as the only driving force. So this is a different thinking, but to address all these larger scale solution solving.
Yeah, I see. Thank you.
Great. Thanks for the talk. Very interesting. I also had a question on this slide. So the optimization objective that you have there, I think I understand that you're presenting that as just kind of a general abstract formulation, but I'm curious, do you specifically have in mind a problem in which the optimization variables xi, j, k are integer, or are they continuous?
So in my current another working paper, we do solve the classic travel assignment problem. In that case, the travel assignment problem is on continuous flow, path flow, so we can compress that dramatically. But when we have an integer value, then it becomes another degree of the complexity, because you try to just convert the floating point back to 0 and 1, becomes very difficult.
Yeah, that
Because
is
gradient
That's
doesn't
exactly where my mind
exist
was
for
going.
the
the
integer
gradient.
sometimes.
So another thought, since you mentioned Praveen Varaya, he made a lot of contributions in traffic control and optimization, but also power systems.
Yeah.
And so you have power flow network optimization problems, where you have electricity demand and then supply of electricity as well through generators. And then you have constraints that basically represent essentially Kirchhoff's laws across these conductors, the power lines. That is the highway for the electrons. So what's interesting is there's quite a long field, a deep field of research on low rank approximations there, where it's also well.
Yes. Yeah.
I'm wondering if you've come across that, and if there's anything we can learn from solving large scale optimal power flow, which is something that power system operators do on a daily basis to schedule generators to maintain our power network. I'm wondering if there's anything we can learn from that field.
Yeah.
Maybe from Praveen or others.
Yeah. So actually, the first early low rank approximation for traffic signal control was invented by Professor Varaya in 2019. Yeah. So I can send a paper about low rank traffic signal control to you. So I believe he signed a few papers on the power supply system, but that paper stay there, has not been further promoted. But he get a very strong message if you use the low rank to look at all the different traffic movements, left turn, right turn, 12 different directions or movements, clear low rank a long time of the day. So we should not just simply define early morning, late afternoon. We should really capture all the potential transition and then design the signal timing according to those kind of structure deviation is sufficient. So I think he also has a strong. He had a lot of hints for us. We need to just go back to his paper to look at it. And
maybe I have a third question. Is so when you talk about low rank approximation of matrices, it's like it's a linear mapping, as you said, right? But depending on what we're mapping, it could be nonlinear. And
it could be linear, but nonlinear somehow, just allow me to say what a quick response here is for traffic assignment problem, a linear problem for the static assignment is a convex. If I provide a linear mapping, I can still make sure that the reduced compressed problem is still convex. So that's why I'm doing linear mapping. If I introduce a nonlinear mapping, I might violate the original convexity condition. So that was my comment form.
Sorry, I don't understand. What are we mapping from and to?
I map the original path flow to some latent flow.
Okay. Okay, that's fine.
Okay.
I think we're at time.
Sure. Hey, so much. First off, I wanted to compliment you on the presentation. I know for at least all of everyone here who does the dense mathematical work, it can be always hard to present. I really appreciated it. I was told that, but it was much easier to follow than many other science teams. So I just wanted to say thank you for that. The key point at the bottom was a big help. As a result, though, as you can tell, I might have struggled to follow a little bit more than some folks here. And so I apologize if this question is too broad, but I'm curious how you feel the explosion in transportation data that we've been seeing now and is continuing over the next few years might impact your work. So just take the OD pairs as an example. What you've been working with, I'm sure, are the existing, travel demand, the travel demand surveys. We're moving away from that. I'm curious how you feel the approaches you've described here might be used in this newer big data space that we're entering, where it's very uncertain and undefined. I apologize if that's a strong question.
This is a good question, and I try to just really show this slide here. That's why we that. So from this paper, this I call the flow through tensor, because we try to model OD flow, path flow, link travel time, path travel time, OD travel time, all in this kind of tensor format, so that we can provide a mapping for measurement, such as the OD measurement, path flow measurement, link flow measurement from detector. There's also different measurements such as a link travel time. So that paper provide many tensor representation. Try to advocate we need to map all the different data sources together. Otherwise, it's very similar to this elephant and a black man. An analogy. People are looking at a different domain. So we just need to use the multiple data source to capture these, and then enumerating all these variables as a tensor or as a connection of tensor is very important.
Thank you very much. And
thank you.
Thanks for listening.
Great, awesome, thank you.
Thank you.
I'm on MOU.